Okay, once again, good morning, everyone. I hope you can hear me and my screen is visible to you. It's visible, right? Okay. Okay, so you're still in seventh chapter, and in previous session we had seen two types of routing algorithm. We had seen there is something called as proactive algorithm and reactive algorithm. And the difference between these two algorithms is these proactive algorithm maintain their route from source to destination, even if a source or a destination doesn't need any kind of service. Still, they maintain their route tables and route. So it is wastage of bandwidth there that we had seen. And some of the examples that includes in this proactive algorithm, these are some of the uh, algorithms which is supported by this proactive. So we have DSDB, WRP star, CGSR, and GSR, and many more. The characteristic of this proactive algorithm is it always maintain routes. So basically, it is not a good idea because it is consuming your bandwidth. So it is written over here. Then yeah, so there are some routes which are there is no use of it. Still, it maintains that kind of route. So it is not a good idea. Again, then there is a quality of service guarantee related because you see it is easy understandable thing because the route is a fixed route. So a network admin can easily find the loophole or a kind of problem. So it is easy to maintain it. So definitely you will get a quality of service. Then route repair demands and high overhead. Yeah, because uh, high overhead means and route repair demands means as there are routes, as I told you, which never going to be used. So if I am maintaining a routing table, then most of the calculation I have to do for these routes as well, which are not going to be used in future or current. Definitely the calculation is very high. If the calculation is very high, then the high overhead will come. In contrast to those algorithms, we have reactive algorithm. These algorithm maintains the route to destination only when there is a service needed by the source or destination. And some of the examples are DSR, ad hoc, and Tora. So the characteristic is simple. It's very scalable because it's a cloud computing kind of thing. So that's why it is very scalable in nature. Then route information when needed, then and then only the path is going to be generated. So we have started one algorithm from the proactive algorithm, that is DSDB, which is a destination sequence distance vector algorithm. You see how this algorithm is work is we need to understand first of all the distance vector routing algorithm, DVR. So in the previous session we had seen some of the aspect of it. So suppose if this is the network topology and this is a routing table by each node, which says that what is the hop count uh, to your neighbor or to the destination or every node. So if A is there, then to reach B, I need a hop count of 1. To reach C, I need a hop count of 1. And to reach D, as I do not have a straight path to the destination D, I will write infinity there. The same way for B, the same way for C, and the same way for D. The routing table is being managed. And now the first step is when A is going to broadcast its routing table to its immediate neighbor. So there are two immediate neighbors, B and C. So when it broadcasts its routing table here, as it has been seen, then what is going to be here in the B routing table? Initially, there is no direct path from B to C. That's why we have infinity. But now, as A table comes up, he can know that I can reach to C via A. So what he gonna do? He will increase the hop count by 1 by going to B to A and then going to A to C. So now the new table is going to be C to 2. Still, there is no way I can reach to infinity because, sorry, I cannot reach to D as it is written infinity. And the same way it is seen that in the A table, A is also not reached to D because there is also infinity. So he's going to leave this blank as a D infinity, right? The next step is for the C table. So when it is shared or broadcast the table of A, it will see that initially I cannot reach to this, what do you call, I cannot reach to B because there is no straight path, but I can reach to B via A. So he will update its table by saying that B equals to 2 by 1 plus 1, 2. So this is a new table for C where he can directly reach to A, no problem, 1. Now he can reach to B by 1 plus 1, 2. And he can directly reach to D, so no problem at all. So these are the new table for B and C. In the next step, what will happen? The C is going to broadcast as table. So you can see here that so there is no way you can reach to this D from A, but as C broadcasts its new table to A, he will find that C can reach to D by 1. So via C I can reach to D. So I will update my table with B1, C1 and D2. So this is a new update for A. The same way is going to broadcast its table to D, where initially he cannot reach to B and A. There is no direct path, but with the help of C he can reach to these two nodes A and B. So he has updated its table. And uh, this is a new or updated routing table for all nodes here, and you can see there is no infinity, right? So every node can reach to any other node via these intermediate nodes. Okay, so this is a distance vector routing algorithm. uh, but we need to think about another uh, problem here that I told you earlier, that there is a specific problem in distance vector routing algorithm. By the way, this is a distance vector routing algorithm, so don't think that this is a DSDV. Still, it has not come here. So I'm right. Distance vector routing algorithm. This is it. And when I reach to here, so now we need to discuss what is the problem, right? So earlier, I hope that you had seen this network topology as well. There is A, there is B, and there is C. And each node is maintaining some distance vector routing table. There is destination, next hop, and count that you had seen, right? I had not taken the diagram, but no issue here. I'm going to give you the problem here. So what is the problem in distance vector routing algorithm? Let's see. Problem in distance vector routing. Suppose there is a node A, there is a node B, and there is a node C. So only 3 nodes we are having, and I'm gonna say this is A, this is, and this is going to be. So I have 3 nodes. Now let's connect these nodes. This is connected. Okay. So now, as I told you that in distance vector routing, every node has a routing table. So I need to give that routing table as well. So routing table has 2 columns here. Let's say the destination, and the another one is let's say count or hop count, whatever you preferable to write. So destination and route count, hop count. So you see for A, there are 2 destinations. One is B and another one is C. So I'm going to write like C and then B. Another thing is the count. So what could be the count to reach C? So if both uh, nodes are having a cost metric of 1 and 1, so I can say that to reach C I need hop count of 2, and to reach B I need a hop count of 1. That's an easy way to be, right? So it's an easy thing, I guess. Now the same thing if I do for this B, this is B. Then there are two destination for B. One is A and another one C, right? So I'm gonna put here that one destination is A and another destination is C. So this is C. And to reach A, I need a hop count of 1. To reach C, I need a hop count of 1. The same thing I'm gonna apply for the C here. And for C, there are another two destinations. One is B and another one is A. This is B, another one is A. And to reach B, I need 1. Sorry. And to reach A, I need a hoop count of 2. So this is the initial phase here. So let's say this is the very first step where my network topology looks like this, and it's a simple thing. Now suppose if somehow in the future, what generally happens is, let me take this one here. So this is the hoop count of 1. And let's say in the future, this link is somehow gets broken. Okay, so this is now broken link. So there is no path between B and C. So this is a broken link here, and you see that it's a broken link from B to C. All right. So now according to that, my destination and count is going to be updated. So there is no problem in the A because there is a link available. So this table is not going to be changed or modified. No problem. However, the change is here. You see that there is no outgoing link to C. So I'm going to update here. I'm going to update for this C. So I'm going to write that there is no path. That means it's an infinity. The link is broken here, right? So that's why here. However, as C is completely, is not contact with any of the nodes, so the table is going to be static. It is not going to be changed. So this is the next step if the link gets broken, and you will see that this will completely uh, affect the whole routing algorithm. So now the condition is when A broadcast is routing table, when A is going to broadcast as routing table to B, to its immediate neighbor, right? This is what we deal in distance vector routing algorithm. So A broadcast its routing table to its immediate neighbor. I guess this is the right spelling. I think there is. Okay, so now this table here, this routing table is going to be copy and pasted here. So this is the A routing table. You see that when I place this, when I broadcast this table to here in the B, now you can easily say that uh, initially there is actually no path between B and C, but by seeing this table of A, B will think that A can reach to C with the help of cost metric of 2. Now if I add one more to this, then I can reach to C, right? He will think that. So he will update its routing table by C to 3, right? So what will happen is he will assume that I'm gonna uh, he will assume like this. This is A, then this is B, and this is C. A, this is B, and this is C. Then this is the path. So now you see that this is the 2 here. So B will think that as A can reach to C with the help of 2. Now if I add 1, then I can reach to C also by moving in this direction. So first of all, I'll go here by 2, and then I will go from here to here directly with the hope count of 3. So I will update this routing table to something like gonna put A to 1 and C to now going to be, I think, right? So this is a new table. This will happen after the A broadcast as routing table. Now you see that there is actually no path, but still B is assuming that I can reach to C. This is not going to be accepted, right? This is first case, no problem in it. Still, there is not a big difference here. I mean, he had just created a problem, but it's a simple problem, and I can resolve it. But now what will happen? As I told you, immediate neighbor can update its routing table to its immediate neighbor. So now there is a chance that, not chance, but this is going to be happen. This is the first. And now what will happen? The B is going to broadcast this routing table, this new routing table to this A. So now the condition is this is the second part. B is going to broadcast. Uh, so I'm gonna take this new table here. Oh, sorry, this is actually B. Uh, this is going to be broadcasted here. So maybe here. So now you see that when A, it's okay. So now when A will see this, actually ये पूरा cut हो रहा है. Here I'm gonna take this. Maybe this is okay. So now you see that when A will see this routing table of B, he will think that initially I reached to C with the help of 2, but now with the help of B, I can reach to C with the help of 4, right? He is going to increment 1 for its route for its hop count. So now he will create a new table and think that I can reach to C with the help of B by 4 hop count. And this is a new table for A. This is a new table for A, which says that there is A, sorry, this is B1, no problem. And for C, I can reach to 4. And you see, this is going to be continuous. Now, the next time A is going to broadcast its routing table, and B is going to update its routing table by C equals to 5. And then B again going to broadcast its routing table to A, and A is again going to change this hop count to 5, and then 6, and then 7, and then 8, and it leads to an infinity problem here. So this continuous updation leads to a problem. Continuous updation leads to a problem known as, I hope you know this, leads to a problem known as count to infinity. Now, you get this problem. I do not know whether you understand or not, but I tried my best to explain you. Please tell me that you understand it or not. This is known as a count to infinity problem, as you are sharing the not updated link. You are just sharing the routing table, and by just looking the routing table, you are changing your hop count by looking the routing table. So that leads to a problem called as count to infinity. Please tell me that you get the count to infinity problem or not. Uh, Anyone, please? Uh, no doubt, sir. Okay, thank you. All right. So you see that there is this is a problem, count to infinity problem. Now to resolve this problem, they have developed another algorithm which I was saying, that this is a destination sequence distance vector. So they keep on broadcasting and increasing their table hop count to infinity, and hence count to infinity problem. So this is it. And to resolve this problem, we have PSDV, which is a destination sequence distance vector. So this is the algorithm. This is the algorithm that we're gonna see in this session. So now this DSD, what will happen now? Another analogy, I'm going to put it over here. Okay, so now let's say we are getting destination sequence distance vector. This is DSD. All right, let's understand. Now what will happen, as you see that there is A again, then B again, then let's say I have also there is a C, and then the last link of last node of D. So they all are connected in a linear fashion. So this is connected to this, connected to this, connected to this. Okay. So now I'm gonna put it over here that this is A, this is B, this is C, and this is D. So we have 4 nodes here. Okay. So now what could be the table here? So table entries are I'm going to put here table entries. So first of all, there is a destination. So I'm going to put it here. So no way, I'll say that what could be the entries here. So first is the destination. Then there is a next hop. Okay, this is next hop. I'm going to separate it with a line. Then there is again a line. There is a metric, that means cost, and again separated by sequence number. So this is a new entry here uh, in the distance vector, destination sequence distance vector. So this is a new entry here. So this is your routing table. So this entry I'm putting over here. So let's say the destination for A is, let's say the destination is this now D. Okay, so only one destination. So this is D, and the next hop is going to be for A is B. The metric to reach D is 1, 2, and 3. So there is 3, and the sequence number. So I'm going to say that D dash 100. The sequence number is completely on you. What sequence number you are using, that is no provision on it. But this is the routing table for A. The same routing table for B is going to be appended over here. So the destination is D. The next hop is C. The metric to reach D is going to be 2, and the same sequence number D dash 100. All right. Now for the C, it is going to be like this. So D, then D, destination D. The next hop is D. To reach D, I need a cost metric of 1, and the sequence number D 100. All right. Now for D is going to be nothing like that. So it is going to be like 0, 0. Or infinity 0 D100. All right, so this is an initial thing. I'm gonna take this thing so that I can later compare it. This is the initial thing. So this is the initial thing, and now what will happen? Let's say that there is a case that this link, C to D is completely gets broken. So I'm going to write it down that the link is broken. Broken link. So you see that the only person here, the only node here which knows that there is a broken link is this C. So when C gets to know that there is a broken link, he will just change the sequence number. He will completely change its this table here. So what could be the updation? So updation in the routing table, earlier it was this was this. Here I'm gonna write. So this is D, D, then cost is 1, and then D 100. This is what the updation is going to be like this. D infinity, because you see there is no path. So the cost is going to be infinity here, and the sequence number, which is very important. So D101. Okay, so this is the sequence number. Now he has updated because there is a link, a broken link between C and D. So this is the only person, this is the only node to update the sequence number. He will only do this. So now what will happen? So now when this B is going to broadcast its routing table to C. Let's say the case is this. When B is broadcasting, B broadcast its routing table to its neighbor. What will happen here? That B is sending this information, DC to D100. But you see that C will know. How you know? Because when this D100 comes up, C will say that this is an outdated information in the B's routing table. This is not the correct information, right? C will know that entry is outdated because D sequence number is increased here, D101, but this 100 is previous. I mean, it's an outdated information. So C will say that please delete this entry, and I will share my broadcasting table or routing table with you. Please update your entry. C will inform it. Okay, so here I'm gonna put all those things. C will know. Okay? C will know that the entry is outdated as D is 101 and B had sent it D100. And it will not update. Okay, it will not update in its routing table. That's a good thing. Instead, it broadcasts the table to its neighbor. That means B as D infinity. You cannot reach to D now because there is a link breakage, and D101. This is the information that the C has now passed to the B. Please update the routing information here because D is not 100, D is 101. Now B will understand, and here now B will understand because of sequence number, and it will delete the previous entry of D100 and update it with new entry from C, that is D101. Okay? And this thing, oh, I'm so sorry. And hence, this will resolve the count to infinity problem. Right? So, is it clear or not? As you can see, it is not just seeing the राउटिंग टेबल, वो सिर्फ राउटिंग टेबल देख नहीं रहे लेकिन समझ भी रहे हैं। क्यों? क्योंकि हमारे पास अब सीक्वेंस नंबर है। सीक्वेंस नंबर को देखेंगे कि भाई ये 100 तो प्रीवियस एंट्री है, लेकिन पहले से ही यहाँ पर किसी ने सीक्वेंस नंबर अपडेट किया हुआ है। दैट मीन्स देयर इज अ प्रॉब्लम। ओके, फॉरवर्ड में कुछ प्रॉब्लम है। दैट्स व्हाई देयर इज अ सीक्वेंस नंबर इंक्रीमेंट। जब भी लिंक ब्रेकेज होगा आपका सीक्वेंस नंबर इंक्रीज होगा, ताकि प्रीवियस नोड उसको समझ सके। और इस तरीके से आप काउंट टू इन्फिनिटी प्रॉब्लम से यहाँ पर बच पा रहे हो। So, do you find any problem here? If you find any problem, please tell me. This is your DSDB algorithm. Anyone, any doubt in it? Okay, I think. All right, no problem. So one algorithm, yeah. So one algorithm from proactive we have understood. It's a very long, lengthy explanation. See, generally people try to avoid everything. See, they generally explain this DSDV, all right, directly. Destination sequence distance vector. वो क्या है? आपको सीधा ये लोग ये diagram बता देंगे. But I had explained you in a very great detail. I hope you can remember it. I mean, it's not that very hard. It looks like very hard, but doesn't look. Uh, so this is your destination sequence. Now, this is one algorithm we had taken from proactive. Now, one algorithm we will take it from reactive algorithm. So I'm going to put it over here that this is a proactive algorithm. I'll say that this is a proactive example. Now let's take one example from reactive and let's complete this chapter here. So the next chapter is AODV, which is known as ad hoc on demand distance vector. Only two algorithm, no problem here, right? Reactive algorithm, reactive example. This is your next algorithm, and this is not going to take much time. You see, as I told you, what is a reactive protocol? Reactive protocol, I'm sorry, is a kind of protocol when you need a kind of something or service. There is a, at that time the path is going to be searched and being put it over here. So whenever node wants to send something to other node, at that time they search for the path, otherwise not. This is a simple explanation that you I think know. So this AODV is an extension. You see, it is an extension of what algorithm? Not DSDV, but something called as DSR, dynamic source routing. DSR, which is I'm gonna write here, dynamic source routing. See, actually, whenever we are teaching mobile ad hoc network, this complete chapter, there are three algorithms. Most probably, every person will try to explain you three algorithms. But in your course, this dynamic source routing has been not there. Okay, it is a reactive algorithm. It is not there in your. I think it's proactive. It is not there in your course. But still, I'll just give you the glimpse. The glimpse is the problem with this dynamic source routing is it sends the path information as in your data. So what I mean to say, so you see that whenever a node find out uh, the path for destination, it will include the path information inside the data. So what I mean to say is, let's say DSR, what will happen if there is a node, I'm sorry, there is a node, there is a node, and there is a node, right? So, and this is the analogy. Okay, so three nodes are here. So what will happen when this A wants to send something to B, okay, and B wants to send something to C. So you assume that these arrows are having only data, all right? You think that there is only data inside this arrow, but not in the case of DSR. It also sends in data your path information, which means that uh, A will forward this data to B, then he can find this B with the help of this path information. उसको ये पता कैसे चलेगा B कहाँ पर है with the help of this path information. और इसकी DSR की प्रॉब्लम ये है कि ये डेटा के साथ आपका path भेजता है. So every data has the path information, and this is the problem. This is the problem of DSR, that send the path information with your data. Now, can anyone tell me that what is the problem here? I mean, it's okay. I mean, to send the path information with your data, but what exactly is the problem? Anyone? I mean, data ke saath path information is okay, but still there is a problem. Can anyone tell me the problem here? It's a simple problem if you analyze it. Very much data on a link. Okay, somewhat correct. Anyone else? You see, the problem is I had drawn here three node. So तीन node के लिए आपका path information क्या होगा? बहुत ही छोटा होगा. Maybe in bytes I think. Okay, बहुत ही छोटा. लेकिन आपका इंटरनेट या आपका नेटवर्किंग है जो डिस्ट्रीब्यूटेड नेटवर्क वो बहुत बड़ा है और उसमें पाथ इंफॉर्मेशन बहुत बड़ी बड़ी होती है. सो अगर आप वो पाथ इंफॉर्मेशन डेटा के साथ भेजोगे तो जितना बैंडविड्थ आप डेटा को पास करवाने के लिए लगाते उससे ज्यादा आपको अपनी बैंडविड्थ पाथ इंफॉर्मेशन फॉरवर्ड करवाने में लगेगी. ओके, सो हम डेटा को तो सेंड कर नहीं पाएंगे और साथ ही साथ पाथ को भी नहीं कर पाएंगे. देखो प्रॉब्लम क्या होगी, कुछ ऐसी होगी कि आपका इनिशियली क्या होता था, कुछ ऐसा कि भाई कि कुछ ऐसा होता था कि सपोज हमारे पास डेटा थोड़ा सा ही है यहाँ पर. सपोज दिस इज डेटा हियर. This is a part of data, and this is the path information, right? But what will happen here is as your network grows, you see, as the network grows, and it is always going to be growth, then what will happen is the situation is going to be like this. The same thing, but now the data is that only. This is the data, but your path information, you can see the this is your path information. It's huge because your network gets grows. So here as the network, right? So the problem is simple. So जैसे जैसे आपका नेटवर्क ग्रो करेगा आपकी path information बड़ी होती जाएगी. Therefore the bandwidth is wasted for the path transmission, okay, rather than the data transmission. So आपका यहाँ ज्यादा से ज्यादा आपका bandwidth कहाँ time consume करेगा? To send this, to transmit this path information rather than to have a data transmission. Okay, so this is a problem here in the DSR algorithm, and this is not acceptable. I'm gonna write it down here that, but problem is as the network size grow, length of path is also increases. Therefore, most of our bandwidth wasted for path transmission rather than data transmission. It's a problem, right? And hence, we have evolved to AODV. Okay, so AODV as a broadcast route discovery mechanism. So this algorithm has a broadcast route discovery mechanism. It is working on a very good routing table. Rather than to have a simple routing table, it has a very complex routing table. And he's gonna send two things here. So has two things. One is known as RERQ, is known as route request a packet. And another one is RREP, which is a reply packet, route reply packet. And so this route request packet is going to use for broadcast. It's a broadcast to find a route. And this RERQ is a unicast packet, which means a single packet coming as a response from the destination. Unicast has to set up forward. Now, so this RERQ जो packet है आपका वो कैसा दिखता है उसके अंदर क्या क्या information होती है? So it is having like this, the information such as source address and source sequence number, broadcast ID, destination address, destination sequence, and there is something called as hop count. This is a broadcast packet, right? So this is a RERQ. The same is for RERP, which is a unicast packet, and it has something like source address, destination address, destination sequence number, and there is hop count and a lifetime. So it's a time to live packet address. Okay, so this is the information you will get inside RERP. Now let's quickly create a diagram of it and let's complete this whole thing. So if I have a network topology such as maybe there is a I'm going to take a gray color. Gray is fine. There is C, there is D, and then there is E. So let's say this is a network topology. So this is A, this is C, this is. Okay, so remember that these are connected. Some again going to connect it. These are connected. You see that initially A is going to broadcast here. A is going to broadcast the RERQ. Okay, so what it is having in the packet. So as I told you that RERQ is having source address. The source address means we're gonna take it in the blue color. A, this is the source address. Then there is a source sequence number. So let's say source sequence number is 1. The broadcast ID, let's say the broadcast ID is also 1. The destination address, my destination is E. So this is my destination, remember. So this is E. Then destination sequence number. This is I do not know because destination still the packet is not reached to destination, so that's why it is going to be dash empty. And the hope count. So the hope count is also I do not know because this is a dynamic route, right? No one knows when the path is going to be generated. So this is also going to be 0, right? So this is my RERQ packet, and this is going to be broadcast. Okay, so this is going to be broadcasted in the to the nodes here, and every relevant nodes the hope count and all is going to be changed. Okay, so you see that here I'm also going to write that this is a source here, and this is going to be destination. So that's why we had written here E. This is important. So when it reaches to the E, so E is having, you know, again the same thing, E A 1 1 E. We have a no hope count because sorry, destination sequence count is still not to be calculated. But when it reaches to the E, it is say that this is a hope count of 1. I reach to hope count of 1 with the help of E. All right, so this is going to be RERQ. There is no subsequent hope count given to C and D, directly hope count given to here. Okay, this one. So this is a RERQ, simple RERQ broadcast. Here. And what could be the RERP reply? So let me remove all these things. So now we will see that destination reply RERP. So what could be the RERP? So here, first of all, as I told you in RERP, what could be the things? Source address. The source address is going to be E. Then there is going to be a destination address. Destination is A, because now this is a reverse process. So destination is this and source is this. And then you see that there is a destination sequence number. He will now append its destination sequence number, that is, let's say 120. And then let's say the hope count. So hope count is 0 because still it is here only. And now when it reaches to the D, it will say that this is E, A, 120. This is destination sequence number and a hope count 1. And when it reaches to C, E, A, 120, and the hope count is going to be 2. There is a lifetime also, which is not I'm not appending here, but that's okay. E, A, 120. So this is your RERP reply, unicast reply. This is your AODV. Okay, and please remember that this chapter is also having prims and crystal. Now, tell me, do you find any problem in AODV or any other algorithm or any topic in this chapter? This is the end of the chapter 7. Any problem? All right, so this ends your complete chapter. Please remember that we have prims and Kruskal also. This algorithm is been there. You already know this algorithm from your data structure and algorithm chapter. So please find some good examples because this is very simple. I hope it is not in your course, but when we are dealing with routing, it always going to be there. So there is a question relevant to prims and Kruskal. So please remember that. Any example that you know you can draw in the exam and can solve it out and just get the marks. All right. So straight away I'm gonna put this in the e-content section. Yesterday Nesh had requested for that, so let me do it. So yeah, I'm gonna do it, and no problem. So thank you so much, guys, and I'll see you in the next session with the next chapter, 8th chapter. All right. So thank you so much. I'm gonna share this file in the e-content section. You can get it from there. All right. Thank you so much, guys. Thank you.